Hi, I'm Bruce Kessler, and welcome to Math Matters. This is a bold experiment for this math teacher to kind of work in front of cameras in front of actual students, but hopefully things will go very well. The idea here is that I get to kind of answer this tough question, why do I need to know this? And hopefully the program you'll find the program useful. Hopefully it'll help you in your classes, and hopefully hopefully it'll drive you to follow up and learn even more mathematics than you set out to learn. It's kind of my intent, I'll be honest with you. The purposes of the show, the stated purposes of the show, is to illustrate some of the just everyday uses of the math that we teach in the general ed and teacher ed math classes. And on this campus that would be Math 109, 116, 211, and 212. It's really a show for students in those courses, perhaps for students who had those courses and are curious about some of the mathematics there and how it's used. But in a broader sense, this is a program that's for anybody interested in mathematics, how it applies to the real world, and hopefully I can bring you some great examples of that. The title of the program, why do I need to know this? Well, it comes from this question we get, and it's one of the toughest questions we get as math teachers. And I'll be honest with you, sometimes we're a little defensive about this question. Hopefully it's born out of curiosity. I was a curious kid and I asked this question. But sometimes that question is born out of a desire to not really learn the material, and you're looking for some kind of excuse. And when the teacher can't provide a good application on the spot, you've got that excuse. So we get a little defensive about this from time to time. The other thing is that a lot of the math we talk about in those general ed courses is there to prepare you for more advanced math that has some extremely cool applications. And that's the kind of math that we focus on as math teachers a lot of times. So we may not have that great example of how the simple math, the easier math, is applied in the real world. That's my job. That's what I'm here to do, is kind of show you some of the cool applications that pop up. Now I have to warn you, you can always come back with this response, well, I don't need to know that because I'm going to teach social studies to first graders and these kind of things. It's true that if you aim low enough, you can avoid using mathematics, at least in your career. A lot of the menial kind of minimum wage jobs that you come across don't require much of a knowledge of mathematics. But let's get real here. I mean, you're in college. If your life's aspiration is to work at a place where they have pictures of the food on the register, you don't need a college degree for that. So I'm assuming right off the bat that you're not aiming low. You're trying to get that high-paying job that requires a college degree. And I'll tell you, even if your career doesn't use math, it's nearly impossible to avoid it in everyday life. The things we do just to function involve mathematics. If you want to buy a car or a house, very few people can walk up and just write a check. You have to borrow money to do that, and that requires a knowledge of interest, compound interest, amortization, those kind of things. If you have money and you want to invest, you need to understand the pitfalls of that. They're constantly bombarding us with survey data in the papers, so you need to be able to understand those kind of things. Political polls. There's no end to the things that we're hit with that require just a basic understanding of mathematics, and hopefully I can bring a lot of those things to light. So I'm assuming we're not aiming low, and that we are going to probably focus on some careers that require a basic understanding of mathematics. Most careers that would require a college degree will require some knowledge of mathematics. Now there are some things Maybe you're going to be a counselor or something like that, and you think, well, I really don't need much math for that. And that may be the case. That's fine. But then we have to deal with just surviving and the things I talked about, like borrowing money and those kind of things. So it goes beyond just the career that we're talking about. We're also talking about being able to function in society, being a productive member of society. And a lot of the examples I show will kind of focus on that. This is just something that you need to know regardless of your career. Those kind of things. The most important thing, though, is that you train yourself not to get taken by folks who have a better understanding of mathematics. If you're willing to always take numerical information from someone else and believe it, then you're setting yourself up for to be conned, basically. I mean, ask MC Hammer where his money is today. Well, his accountant took it and it's gone. These are the kind of things that, where if you've been paying a little bit of attention, perhaps he could have stopped. Just being able to spot a bad answer. I can give you a great example of this. One of the houses that we sold, we went to the office to sign all the paperwork to get our money and these kind of things. And I had already kind of run these numbers. And so when the bottom line was laid out and they had the check all cut and laying in front of us, I thought, that number doesn't sound right to me. And we had them go back and check, and it turns out that when they had called for the payoff amount from the bank, they had scribbled down the number. And the person couldn't read his own handwriting. He had put down the wrong digit in the thousands position. Well, that wrong digit was 1,000 less than I was supposed to receive. That would have cost me $1,000. And we can hope that they would have been on the ball and realized at some point their mistake and corrected it. But there's no guarantee of that. I caught the mistake because I had a general kind of knowledge of the way things were working and how much money I was supposed to receive. So I was my best defender in that case. The big thing is that this program is there for you. It's intended to help you. And for that reason, I'm going to ask you to give me input on this. Tell me things that we've done that help, things that would make the program better. If you come across some math in one of your courses that you don't see a good application for, ask me the tough question. Say, why on earth would I need to know this kind of stuff? And I'll do my very level best to answer it. I have kind of mapped out things that I want to talk about, but if you come up with something better, then I am more than willing to go with what you've got. We have an email address there, and we have a web page that we can be contacted at. Please use those. One of the first things covered in a general mathematics course typically is a little bit of information on sets. And it's presented as a pretty abstract thing. We eventually get around to some good uses for it. I want to show you an example today of how a knowledge of sets, and in particular a little trick called Venn diagrams, can be used to help in resource management. I'm going to give you a little situation and show you how sets can be used, a knowledge of sets can be used to kind of solve the problem. Here's a situation for you. Let's say a business has 100 non-clerical workers. These are R&D people, sales people, whatever it is. And they have certain resources at their disposal. We've got 40 administrative assistants that can be spread around to these 100 workers. Perhaps they're going into a new building where they're going to have 24 little labs that folks can use. and they're going to make a laptop purchase. So they've decided they're going to purchase 60 laptop computers. And the question is, if you're, let's say you're the office manager or something, or the someone in charge of allocating these things, the question is, how do we allocate these things to kind of spread it around? And certainly, you know, if you add 60 and 40, you've got 100. So there's enough to go around. But to complicate things, upper management has some minimum requirements here. They've determined that 10 of those 100 people need all 3 of these resources. And they probably know exactly who they are. So you don't have to decide that, but you have to live with that. They've determined that 4 need only an administrative assistant and research space. They don't need a laptop computer. They're not mobile. They're okay. They've identified 10 people who need only research space and a laptop. They don't need a secretary to handle situations, set up interviews or whatever that is. And they've identified 11 people who need only an administrative assistant and a laptop. Maybe these are sales folks that need help setting up appointments and those kind of things, but they're not involved in any kind of R&D, these kind of things. So you've got to live with these constraints. These are minimum constraints on the way that the resources are allocated. Well, the idea with Venn diagrams is that you use circles to represent sets. And I'm using this big box to kind of say everything's going to happen inside this big box. So I could use a circle then to represent folks who receive an administrative assistant, and a circle for folks who receive research space, and a circle for folks who will receive a laptop computer. And what we do is we arrange these circles so that they can overlap and interact with each other. So when we look at these minimum requirements that are being handed down from upper management, the 10 folks that will receive all 3, well, these are the folks located where all 3 of the circles overlap right here. And so we could just fill in that number. And I'm going to put a little up arrow there to say that that's a minimum. That number could go up. You know, if we have enough resources, we could make that number larger. The 4 who need an administrative assistant and a research space, well, that's where these 2 overlap, but not with the 3rd one. So that would be right there. And again, I'm going to indicate that that number could go up. The 10 that need research space and a laptop, right there. Okay. And that could go up. And then the 11 who need an administrative assistant and a laptop, that's right there. Okay? Now let's deal with the resources that we have available. We've got 40 administrative assistants that we can pass around. That means that the total of numbers inside this circle needs to be 40. So to see how many go right here, I just need to subtract the things I've already allocated from 40. I think that's 25 allocated, so that leaves us with 15. And that number could go down. If these go up, that would have to go down, right? The 24 folks who can use research space, well, I've already allocated all 24 of those. So that 0 there means nobody can go get just research space. And it's not just a maximum, it's also a minimum. I can't go below 0 people. So that pretty well locks in then the other numbers, okay, inside that circle. The 60 who can receive a laptop, well, I've already allocated 31, so that leaves me with 29. And then the last one, you may not have thought of this, but the folks who receive nothing are these folks in the block but outside the circle. So if I just take 100 and I subtract all the different amounts that I've allocated, I think that leaves me with 21. So with the current structure, I've got 21 folks who receive none of the 3 resources. And what you'd like to do as a office manager is you'd like to minimize that number. So you go back and you say, you give them this answer, they're going to say, no, that's too high. We've got to get that number lower. Well, you can actually show that this is as low as it can get. Let's say I go back in here and the only number I can really raise here is the 11. So I go up to 12 folks getting both an administrative assistant and a laptop. Now the effect that has is it lowers, right? If I raise this one by 1, I've got to lower this one so that they all add up to 40. And I have to lower this one so that they add up to 60. Okay? Well, the effect, and everything has to add up to 100. So I've got, I've added 1, subtracted 1, subtracted 1. Guess what? I have to add 1 there. So if I make the only change I can make, it actually makes that number larger. And so you can go back and defend that answer and say, well, that's the best I can do given the constraints you've given me. It also enables you, if you play with this a little bit, to say, look, if you really want that lower, you've got to do that. You've got to change the overlaps. You gave me minimum requirements. If you go back and you change that, I think this was a 4 before, if I lower that to 3, okay? Well, that means I can raise this number by 1. It means I can raise the number of folks getting research space only to just 1. And then I think that number would stay the same. But when you add all those things up, I've subtracted 1, added 1, added 1, subtracted 1. So that number's 1 lower. And so if they're willing to reduce the doubles, the folks getting 2 of these resources, you can reduce the so-called withouts by 1. If they go through and reduce the number receiving all 3 of these things, okay, that makes changes in then each of the circles. That number goes up by 1. That one goes up by 1. That one goes up by 1. And that causes then a change of 2. The original answer was 21. That comes down to 19 now. So if they reduce the triples, that can reduce the folks without resources by 2. So if they really want to lower that number, they can go back then and change their minimum requirements for folks receiving both of those things. That's a nice little example of resource management. It comes from a basic knowledge of sets, and that's exactly the kind of stuff that we teach in that general math class. And I'll flash some things up here on the screen then to kind of summarize what we talked about. One last thing I want to talk to you about today, in the algebra courses right now, you're probably going back and reviewing exponent rules. And when we do this, this is very basic stuff. One of the first questions I always get on this, why do I need to know exponent rules? I mean, it seems so dull. And I'm with you, on the surface it seems a little dull, but I'd like to show you an example of where exponent rules are used, and it involves understanding investment strategies. And eventually I'll leave you with a good little rule of thumb that you can use for investment purposes. I should flash these up, the exponent rules. If you take two things of the same base and they're both raised to a power and you multiply them, you can add the exponents. If you divide, you subtract the exponents. And if you take something raised to a power and you raise it to another power, you actually multiply the exponents. And that's the kind of thing that you practice, you know, in your homework assignments and those kind of things. Well, suppose you have some set amount of money that you want to invest, and it could be a compound interest account with a bank, or it could be a mutual fund, some kind of investment like that. Maybe they're offering you 4%, which would be a pretty good rate for right now. A good question would be, how long does it take to double your money? I mean, that's something I would want to know. If I'm going to throw this money in the bank and not spend it right now, I'd like to know how long I have to wait for it to double. And then they sometimes offer you things that are compounded more often. How important is that to the accumulation of money that I'm going to get? What if I can get 5% somewhere else? Is that going to make a big difference in how long it takes it to double? I mean, that's a good question. Maybe I get a little risky and decide to put some money in stocks or bonds or something. I can get 10%. Will it double, and will it take half as long to double? I mean, that's a good question. Well, let's work this out. This is what I want to kind of work with here, and it involves a knowledge of how we calculate interest. And a little terminology, the idea of principal, okay, that's the amount that you invest to draw interest on. And then to calculate interest, you take your principal and you multiply by the rate and the time. Now, the rate we convert to a decimal before we do this, and the rate and time have to be for the same unit. So if we're talking about time in terms of years, then we want to use an annual rate. That's the kind of thing I'm talking about. And I can write that shorthand as P times R times T. P for principal, R for rate, and T for time. To get your new amount, you take your old amount and you add the interest. So I actually can write that kind of as a little expression. P is your principal plus PRT. Well, I can factor. This is a little algebra trick. I can pull a P out of each of these, and it leaves me with a 1 plus RT. The reason I show you that is I'm going to use this formula in just a few minutes here. Now, this business of compound interest, that means that after a certain period of time, I take that interest and I add it to my principal. Then the next time, I don't take it out of the bank or I don't uninvest it. I take that new amount then as the principal for the next pay period. That's kind of the idea. So you accumulate money and you actually draw interest on your interest that way. So if we're doing 4%, this was the original kind of situation, compounded annually, and I'm calling the principal 1. 1 what? $1? I don't know, one chunk of money, it doesn't matter, whatever you want to call it, one pot of gold, whatever it is. Well, at the end of that first pay period, which is 1 year, I've got my principal, and then 1 plus the rate times the time, and that's 1.04. The compounding comes in when you make this amount your new principal, and you do the same calculation again and it goes up a bit. But here's what's happening. This is where exponent rules come in. The original 1.4 is raised to the first power. You've got another 1.4 raised to the first power. 1 plus 1 is 2. So your new exponent is 2. Okay, that's the first exponent rule we looked at. Do it the third year. Again, I raise it, so it raises the exponent by 1. And you keep doing this at the end of the teeth year, that's probably not the best way to think about it, you've got 1.04 then to the t power. And I can actually graph that for you. Go through at the end of each of these years. Let's go back to this. You've got your nice, your dots. That's the amount you have at the end of each year. And I've got a horizontal line drawn here to indicate two chunko monies, whatever that is. So it takes actually 18 years to get above that line. Now, if I go back, here's the other question, what if I compound more often? Well, what has changed in this calculation? It's still 4%, but now the amount of time is 1/4 of a year. So that gives me a different number, 1.01. At the end of the second quarter, I compound this interest again, and this 1.01 becomes my new principal. But again, these are exponent rules, and so as I do this, next quarter it goes up to 3. End of the first year, this is now 4. I've compounded 4 times at the end of that first year. So after the teeth year, it's now 1.01. That has changed, and it's now 4 times t because I'm doing it 4 times a year. So if I go back and let me put these dots right on top of the other, or it turns out they're right on top of the others, it doubles in 17.5 years, not because I'm drawing that much more money, but because now I can get my money out or check on it in quarter-year increments as opposed to full-year increments. But those dots are basically right on top of each other. Now, here's a trick, and this looks like it has nothing to do with what I'm doing, but it does. If you take this expression and you think about plugging in bigger and bigger powers, or bigger and bigger numbers in. When that's 1, it's 1 plus 1 over 1, which is 2. Raise to the first power, that's 2. And then when I go to 10, it gets bigger. When I go to 100, it gets bigger. But watch what happens. It's getting bigger all the time, but some of the decimals start to kind of stay the same. There, there. Getting really big numbers now. It actually levels out, and this is a weird idea. It kind of levels out to this number, 2.718, blah, blah, blah. It's an irrational number, which means it's a non-terminating, non-repeating decimal, and it's hard to write down, so we typically just use the letter E for this. Okay? Well, if I'm thinking about this calculation, this R to the N, I can do this kind of deal. I can replace N with RK. And when I do that, the R's cancel, and here's your exponent rules again. I can pull this R outside, and so this business is the E, and it's raised to the R power. And for t years, again, you just pull this t out, and it's e to the RT. So what I've got is a nice curve that you can graph on your graphing calculator. I don't have to plot these points. I can just draw that curve. That E is a button on your calculator that you can draw. And it crosses 2 at 17 1/3 years. If I bump this up to 5, it does make a sizable difference in the amount of time it takes to double. And if I go to 10, it doubles in exactly half the time, it turns out. Okay? So that's a good little rule of thumb. In fact, it's called the rule of 70. And that is that whatever interest rate you're getting, if you want to know how long it takes to double it, you take 70 and you divide it by that interest rate, and that's how many years it takes. And to kind of show you that, your rate is always, you move the decimal 2 places, that means you're dividing by 100. Well, where 70 comes from is e to the 0.70 is roughly equal to 2. And so if you think about multiplying and dividing by r, this 0.70 divided by r replaces the t. And so t turns out to be 70 divided by k. So it's a nice little rule of thumb. It's all the finance people know this rule. If you talk to some kind of financial planner, they'll tell you, how soon do you want this to double? And that'll determine how risky you have to be, what kind of interest rate you have to get to make it happen. Okay, and you can flash up the summary stuff on this as well. Well, that's our first episode of Math Matters. Why do I need to know this? I hope you find this kind of stuff useful. I realized a lot of these things I went through very quickly, so let me just tell you that the segments, all these things you've seen here today are downloadable from our web page, and they'll flash that address up here at the end of the program. Anything that was too quick, you want to go back and check it, see it yourself, go to that web page and download it and look things over. Also, come back to me with suggestions. I'd love to hear from you. And so with that, I'm going to wrap up the first episode. See you next week.